Welcome to Talk Tensors.
It's great to be back.
Okay, so I want to start today with a bit of a visualization exercise. I want you to close your eyes for a second.
Unless you're driving.
Right. Unless you're driving or operating heavy machinery, maybe doing that thing where you walk on a treadmill while you work. But for everyone else, picture this.
Yep.
Imagine a small, pixelated town. If you grew up playing video games in the 90s or early 2000s, it looks exactly like an old-school 16-bit RPG.
I'm thinking Final Fantasy VI or maybe Stardew Valley.
Exactly. You've got that isometric view, little pixel trees, cute little fences. There's a pharmacy, there's a park, a school, a bar, and a cafe called Hobbs Cafe.
Classic cozy game vibes. It feels, very nostalgic.
It feels safe, exactly. And there are 25 residents walking around in this town. You've got John Lynn, he's at the pharmacy. Isabella Rodriguez is working at the cafe. Klaus Mueller is over at the college library.
Okay.
Now, in a normal game, what happens when you click on John Lynn?
You get a text box. It says something like, "Welcome to the pharmacy." Or maybe he gives you a fetch quest to find, 3 herbs.
And if you click on him again 10 seconds later,
he says the exact same thing. "Welcome to the pharmacy." Over and over.
Right. He's a loop. He's a sprite with a script attached. He doesn't know you. He doesn't know it's Tuesday. And he certainly has no idea that his neighbor is planning a party later.
He's not really a character. He's more like a piece of interactive scenery.
Precisely. But in the town we're discussing today, there are no players. And there are no simple coded loops. These aren't characters walking in circles waiting for a user to trigger them. These are autonomous agents. And they're driven by large language models.
So they're thinking for themselves.
They wake up, they brush their teeth, they go to work, they gossip about their neighbors, they form memories, they even plan Valentine's Day parties, and this is the crucial part. They do all of this without a single human telling them what to do.
And this is what we're doing a deep dive on today. This seminal work on what are called generative agents.
Right.
And to be really clear for you listening, this isn't just about hooking a chatbot up to a video game character. That's been done.
That's the easy part.
It is. This is about creating a simulacrum of human behavior that is actually believable over a long period of time.
That's the key phrase, isn't it? Believable over time. Because anybody can get ChatGPT to write a scene where a shopkeeper talks to a customer. That's trivial now.
Yeah, that's a 5-second prompt.
But making that shopkeeper remember the conversation 3 days later and having that conversation actually change how they feel about the customer, that is a totally different beast.
A whole different ballgame. And that brings us to the thesis for today's deep dive. The magic here isn't the LLM itself. The LLM, think GPT-4 or something similar, is just the engine.
Okay, the raw intelligence.
But an engine needs a chassis, right? A transmission, steering wheel, brakes to actually be a car.
Sure.
The core contribution of this paper is the agent architecture. Specifically, we're going to look at the 3 main pillars. The memory stream, the reflection mechanism, and the planning modules.
And these are the components that stop the AI from, just hallucinating? Or forgetting who it is 5 minutes later.
Exactly. This architecture is what solves the problem of long-term coherence. It's the framework that turns a simple text predictor into a believable agent.
So before we get into the nuts and bolts of how John Lynn knows to turn off the stove when his breakfast is burning, let's unpack the problem space a bit. We need to understand why believable agents have been such a white whale for computer science for so long.
It's a great way to put it.
We've had NPCs, non-player characters in games for decades. Why is this so different?
Well, it comes down to this concept of the illusion of life. It's a term that goes all the way back to the early days of Disney animation.
Creating characters that feel real.
Right. Not just move, but feel like they have an inner world. And in gaming, we have historically relied on rule-based approaches to do this. The industry standard is something called the finite state machine, or FSM.
Okay, can you break that down for us? What is a finite state machine in this context?
It's basically just a flowchart. It is deterministic logic. You, the developer, you sit down and write a state. If player is near, then say hello. If health is low, then drink potion. If it is nighttime, then go to bed.
So it's a massive, and I mean massive, list of if this, then that statements.
That is exactly what it is. And the fundamental problem with that is brittleness.
Griddleness.
If you don't write the code for eating lunch, the agent literally cannot eat lunch. It cannot improvise. It can't do anything you didn't explicitly think of and code in advance.
There's that famous example in the game Skyrim. You can put a bucket over a shopkeeper's head and then rob them blind.
Right. And they just stand there.
They just stand there because the developers didn't write a specific state for bucket is currently on my head.
Precisely. The logic tree doesn't cover that one weird edge case, and so the immersion just shatters instantly.
So rule-based systems fail at open-ended interaction because you cannot possibly code for every possibility in the universe.
You can't. So then you have the next approach, which is reinforcement learning, or RL. This is the technology that powers systems like AlphaStar or OpenAI 5 to beat the world's best humans at incredibly complex games like Dota 2.
And RL is all about rewards, right? You get a metaphorical cookie if you do something good. You get a little shock if you do something bad.
Roughly speaking, yes. RL is incredible for adversarial games where there is a clear win state.
Winning StarCraft.
Exactly. Winning StarCraft is an optimization problem. You want to maximize your resources and destroy the enemy base. The goal is clear. But here is the issue. How do you define a reward function for having a nice chat with your neighbor?
Or planning a thoughtful party, or deciding to take a nap because you're feeling a bit down?
You can't. Social simulation is open-ended. There is no score. If an agent decides to become a recluse and just read books all day, is that losing? No, of course not. It's just a different personality.
So RL struggles massively in these environments because the goals are subjective and social. The loss function, the metric of failure, is impossible to define mathematically.
Right. So rule-based is too brittle. RL is too objective-focused, which brings us to large language models. We know they can write poetry, they can write code, they can write dialogue. So why can't I just tell GPT-4, you are Klaus the researcher, go live your life in this town?
It seems like the obvious solution.
You can try it, and for the first 5 minutes, it will probably be amazing. It'll give you this incredible monologue about how much it loves research and the smell of old books. But you will immediately run into what the researchers call the boneless agent problem.
Boneless agent.
Yeah.
That is a visceral image. It sounds like a monster from a horror movie.
It kind of fits. In a cognitive sense, the model has no spine of memory. It has no long-term continuity. It hallucinates.
It just makes things up.
It does. If you ask it to be Klaus, it might say, I love spending time at the library. 10 minutes later, if the context window has shifted or it gets distracted, it might say, I've never been to the library in my life. It lacks a cohesive self.
Because it's just predicting the next word based on the immediate prompt. It has no actual history.
No history at all. So the paper we are covering today introduces the solution to that, an architecture that wraps around the LLM.
Okay, so the LLM is inside this other system.
Think of the LLM as the subconscious processing unit. It's the part that handles the language and the raw intelligence. This new architecture provides the memory, the conscious planning, and the ability to reflect. And they tested it all in this sandbox environment they called Smallville.
Let's dive into that first pillar of the architecture there, the memory stream. This to me sounds like the most sci-fi part of the whole paper. They describe it as a database of the self.
It is the foundation. And I mean that literally. Without the memory stream, absolutely nothing else works.
So what is it?
Think of it as a comprehensive time-stamped list of everything the agent perceives. And I mean everything. This is not just a chat history, it's a log of observations.
Give us a sense of the granularity here. What does a memory actually look like in this stream?
It's stored as natural language. So a single memory object might be something like, Isabella Rodriguez is setting out pastries at Hop's Cafe. Another one might be, the refrigerator is empty. Or even a social observation. Isabella and Marie are discussing a party. Every single thing the agent sees or hears or even does itself gets logged as a discrete memory object with a timestamp.
But wait a minute, I have to push back on the scalability of that. If the agent remembers everything, every time they walk past a tree, every time they brush their teeth, every single idle comment they overhear, that list is going to get massive.
Oh, enormous.
We're talking thousands, maybe tens of thousands of lines of text per day, per agent. And we know LLMs have context windows.
Right, the amount of text they can read at any one time.
You can't just feed a novel's worth of logs into the prompt every single time the agent needs to make a decision. The system would grind to a halt.
You've hit on the central engineering challenge they had to solve, cost and latency. If you fed the whole stream in, you'd go bankrupt on API fees in about an hour, or the system would just crash.
So how do they solve it? How do they make the agent remember the right things without having to remember everything all at once?
They built a retrieval function. The architecture needs a way to filter the noise. It needs a search engine for its own brain.
A search engine for its own brain. I love that analogy.
It's the perfect way to think about it. It has to ask itself, okay, out of these 10,000 memories I have, which 10 are actually useful for what I'm doing right now?
It's like when you're trying to remember where you left your keys, your brain doesn't bother reminding you of the quadratic formula. It filters for relevant information.
Exactly. So the question becomes, how does it rank them? How does the system decide that remembering my wife's name is more important than remembering I saw a squirrel yesterday?
Right. What's the algorithm there?
The paper outlines this really elegant scoring system that's based on 3 specific components. This is the secret sauce of the retrieval system. And the components are recency, importance, and relevance.
Okay, let's break this down one by one. Recency seems pretty straightforward.
It is. It's the most intuitive one. Humans suffer from recency bias, and it turns out that's a useful feature for an AI agent as well. Things that happened recently are simply more salient in our working memory.
So they built that in.
They did. The system uses an exponential decay function. The score of a memory basically drops the older it gets.
Can you give us a sense of that decay rate?
Yeah, in their implementation, they used a decay factor of 0.995 per game hour. So a conversation you had 5 minutes ago has a recency score of basically 1. A conversation from last week might have decayed all the way down to 0.1 or even less.
Which ensures the agent is grounded in the present moment, right? It's not obsessing over some trivial thing that happened 3 days ago.
Okay, it keeps recent events top of mind.
Okay, so fresh memories score higher. Next up is importance. Now, this one is really interesting to me because importance feels incredibly subjective. How does a computer know that eating breakfast is a mundane event, but breaking up with a girlfriend is a core, life-altering memory?
This is one of the most clever parts of the paper. They don't try to hard code a list of important events. That would be brittle, just like the old FSMs.
So what do?
They ask the LLM.
They ask the LLM to rate its own memories for importance.
That's exactly what they do. After a memory is created, they fire off a separate prompt to the model. And that prompt looks something like this. On a scale of 1 to 10, where 1 is purely mundane and 10 is extremely poignant, rate the likely poignancy of the following piece of memory.
That is wildly simple.
It is, but it's incredibly effective. Because the LLM has been trained on, practically the entire internet, it has a very, very good implicit grasp of human social norms and what we consider to be important.
So what kind of scores does it give?
In the paper, an event like eating breakfast gets a score of 2, but something like breaking up with a significant other gets an 8. Your house catching on fire might get a 10.
So even if the breakup happened a week ago, meaning its recency score has decayed and is really low, the high importance score keeps it floating near the top of the retrieval pile. It ensures it doesn't get forgotten.
Precisely. It mimics how human memory works, especially with trauma or joy. I remember my wedding day vividly, even though it was years ago. The importance is so high that it completely overrides the time decay.
Whereas I don't remember what I had for lunch last Tuesday, even though it was much more recent. The importance score is effectively 0.
Exactly. It's a great filtering mechanism for significance.
That makes total sense. And the third component you mentioned is relevance. This feels like the tiebreaker, the context-specific part.
This is the part that connects memory to the current situation. If I ask you, what should we study for the upcoming chemistry test? Memories about your wedding or your breakfast are completely useless no matter how recent or important they are.
You need memories about the periodic table.
You need memories about chemistry. And technically, this is where the concept of embeddings comes in, which is a buzzword you hear a lot in AI circles.
Right. Can you just quickly define that for us?
Sure. An embedding is just a way of turning a piece of text into a list of numbers, a vector that represents its semantic meaning. Words with similar meanings get turned into vectors that are close to each other in a high-dimensional space.
Okay.
So the system generates an embedding vector for the current situation, which is the query, thinking about what to do next, for example. And it compares that to the embedding vector for every single memory in the database. Then it calculates the cosine similarity.
Which is a fancy mathematical way of measuring the angle between the two vectors.
Correct. If the vectors are pointing in roughly the same direction, the concepts are related. So if the current context is planning a party, the vector math will naturally pull up memories related to friends, invitations, and cafe, while ignoring things like work or pharmacy, because those vectors are pointing in different directions in that mathematical space.
So you take the recency score, the importance score, and the relevance score. You put them all on the same scale, you normalize them, and then you add them up for each memory.
And the handful of memories with the highest final scores get fed into the LLM's prompt. That is what determines what the agent thinks about in any given moment.
Okay, so that handles the raw data. The agent perceives the world, it logs it, it retrieves it. But that's still just data, right? It's a collection of facts.
Yeah.
Isabella saw the table, Isabella saw the stove. That doesn't give us a personality. That doesn't give us insight.
No, it doesn't. And that is a perfect transition to the second pillar of the architecture, reflection.
Reflection architecture. Why is this necessary? Why isn't that powerful memory stream enough on its own?
Because raw data doesn't equal understanding. They actually call this the boneless agent problem again in their ablation studies. If you just have a stream of raw memories, the agent really struggles to generalize. It can't see the forest for the trees.
Can you give us a concrete example of how that failure mode would look in the simulation?
Absolutely. Imagine you stop an agent and you ask it, who should you hang out with right now? If the agent only has access to its raw memories, it's going to rely very heavily on recency. It will look at its log and see, oh, I just saw my neighbor Klaus walking past me 5 minutes ago. So its answer will be, I should go hang out with Klaus.
Even if, in its backstory, the agent technically hates Klaus.
Exactly. It creates a very reactive, shallow kind of behavior. It doesn't have the ability to step back and think, hey, I actually find Klaus really annoying, but I love hanging out with Maria because we both share a passion for music.
It has the individual data points, the memories of specific interactions, but it hasn't connected the dots to form a higher level opinion.
It lacks insight. It's living moment to moment. Just like that goldfish we mentioned.
So reflection is the process of connecting those dots. It synthesizes the raw memories into more abstract, higher-level thoughts.
That's a perfect way to put it.
So how does the system generate a reflection? Does the agent just decide to sit under a tree and ponder the meaning of life?
It's actually triggered automatically by the flow of information. Remember those importance scores we talked about?
Yeah, the 1 to 10 scale.
When the sum of the importance scores of the latest events exceeds a certain threshold in the paper, they use a value of 150. The agent essentially forces itself to take a thinking pause.
It's like an internal alarm goes off that says, whoa, a lot of heavy stuff just happened. I need a minute to process this.
That's exactly it. And when it enters this reflection state, the system looks at the last 100 memory records and prompts the LLM to generate high-level questions about them.
It asks itself questions.
Yes. It asks things like, what is the most important theme running through these recent events? Or more specific things like, what is Klaus passionate about? Or how does Klaus feel about Maria? It's interrogating its own memory.
That is very meta.
It is. And then it uses that same retrieval function, that search engine for its brain, to find specific memories that help answer those self-generated questions. And finally, it synthesizes those answers into a new memory object called a reflection.
And this new reflection gets stored back into the memory stream, just like a physical event would be.
That is the beauty of it. To the memory stream, the abstract thought Klaus has dedicated to his research is just as valid a memory object as the concrete observation Klaus is reading a book. They're both just memories.
And this creates a kind of hierarchy of thought. The paper mentioned something called a reflection tree.
It's a great visual analogy. Imagine a tree structure. The leaf nodes at the very bottom are the raw ground-level observations.
Klaus is reading. Klaus is talking to the librarian. Klaus is writing on a notepad.
Right. The system looks at those leaves and it synthesizes a new node just above them. A reflection like, Klaus is spending a lot of time on his research.
Okay, so that's a mid-level thought, a generalization.
Then later, it might look at that mid-level node and combine it with another node about, say, Klaus declining a party invitation, and synthesize an even higher level node. A reflection like, Klaus is prioritizing his career over his social life.
I see. So when the agent needs to make a decision later, like, should I invite Klaus to the bar tonight? It doesn't have to reread every single memory of every book Klaus ever touched.
Exactly. It can just retrieve that high-level reflection. Klaus is prioritizing his career, and the LLM can infer he'll probably say no.
It allows for complex, human-like reasoning without constantly overloading the context window. It's a way to compress experience into wisdom.
That's it. It builds a structured understanding of its own life.
So we have memory, which is the raw data, and we have reflection, which is the wisdom. That gives us a brain with some real depth. But a brain in a jar isn't enough. These agents need to act. They need to live out their days in Smallville.
Right. They need to do things.
Which brings us to the third pillar, planning.
Planning is absolutely essential for coherence over time. Without a plan, the agent is just, a pinball. It's just reacting to whatever's in front of its face at any given moment.
The paper brings up the lunch problem as a key example of why this is so necessary.
Right. So without planning, if you ask an agent what it should do at 12:00 p.m., the LLM looks at the time and says, eat lunch, which makes perfect sense.
Very logical.
But then at 12:30 p.m., you ask again. It looks at the clock, sees it's still lunchtime, and says, eat lunch. And maybe again at 1:40 p.m., because in isolation, eating lunch at noon-ish is a statistically probable action for a human to take.
But eating lunch 3 times in a row is, it's psychotic behavior.
Yeah.
Or at the very least, extremely inefficient.
It completely breaks the illusion of life. So to solve this, the architecture uses a method called top-down recursive planning.
Okay, walk us through that. How does an agent structure its day?
It starts with the broad strokes. When the agent wakes up in the morning, it generates a high-level plan for the entire day. Something very simple. Work from 9 to 5, have dinner at 6, go to bed at 10.
Okay, a basic schedule.
Then, as the day actually progresses, it recursively decomposes that plan. It takes the next chunk of time, say the 9 a.m. to 10 a.m. block labeled work, and it breaks that down into smaller steps. Work becomes check emails, then draft a paper, then take a quick break.
And it goes even deeper than that, right? All the way down to the actual movements in the game engine.
Yes, all the way down to 5 or 15-minute increments. Get a snack from the kitchen, walk to the garden, sit at the desk. This fine-grained action plan is what actually gets translated into coordinate movements on the Smallville map.
But plans change. Life happens. If I plan to work from 9 to 10, but my kitchen catches fire at 9:05, I can't just keep typing at my desk.
Of course not. And that is where the reaction loop comes in. The plan is not rigid code. It's more like a strong suggestion. At every single step, the agent is still perceiving the world around it.
There's a specific scenario in the paper that illustrates this perfectly with John Lynn and his son, Eddie.
Yes, it's a great example. John's plan is to go watch TV in the living room. But as he's walking towards the living room, he sees his son, Eddie, taking a walk in the garden outside. The system logs this new perception. Observation. Eddie is walking in the garden.
Now, a rigid, rule-based system, like those finite state machines we talked about, would just ignore Eddie. The plan says watch TV, so it would continue to the TV.
Correct. But this system immediately runs its retrieval function. It pulls up relevant memories like, Eddie is my son, and the reflection, Eddie is working on a difficult music composition. It then effectively asks the LLM, given this new observation, should I continue with my current plan, or should I react to this new information?
And what does it decide in this case?
The LLM decides, my son might be stressed about his project, I should go talk to him. So John abandons his plan to watch TV, walks over to the garden instead, and initiates a conversation with Eddie about his music. The plan is dynamically updated in real time.
That is the magic moment, isn't it? That interaction wasn't scripted by a developer. It emerged organically from the architecture.
It's the perfect balance between the stability of having a long-term plan and the reactivity you need for a believable, dynamic environment.
So we have the complete architecture, the memory stream, the reflection, and the planning. That's the engine. Now let's talk about the car itself. Let's talk about Smallville.
Smallville is the sandbox. It's the test bed where they let these agents run free. It's a simple environment, 25 agents in total. It captures the basic affordances of a small town. You've got houses, a park, a store, a cafe.
And they initialize these agents with just a single paragraph of text, right? That's all they started with.
Just a seat, a name, a job, and a few key relationships or personality traits. For example, John Lynn is a pharmacy shopkeeper. He lives with his wife, May, who is a professor, and his son, Eddie, a music student. He loves his family very much. He has a bad back.
That's it.
They didn't script his day. They didn't write any of his dialogue. They just dropped him in and pressed play.
And then things started to happen. Emergent social behaviors.
This is where the paper gets really, really fun. Let's start with the election.
The election, right. This was a case study in information diffusion.
The researchers wanted to see if news would travel organically through the town. So they planted a seed with just one agent, a guy named Sam Moore. They told him, you were running for mayor of Smallville.
And they didn't tell anyone else. There was no global announcement, no tweet sent to everyone's phone.
Nothing. They just let Sam go about his day. And Sam, guided by his new goal, did what a political candidate does. He saw his friend Tom at the store and told him about his campaign.
Hey, John, just wanted to let you know I'm running for mayor.
Exactly. And then, and this is the key, Tom went and told John. He thought it was interesting news. And John went home that evening and discussed it with his wife, May. The information started jumping from agent to agent through natural conversation.
It's the telephone game, but with AI. What were the final results? How far did the news spread?
Over the course of 2 simulated game days, knowledge of Sam's candidacy spread from that one single agent to 8 other agents.
8 out of 25. That's 32% of the entire town.
All through organic conversation. The researchers didn't force a single one of those interactions. It just happened.
That's incredibly impressive. It proves the agents are actually communicating meaningful information, not just exchanging canned pleasantries like, hello, how are you?
Right. But the second case study is, I think, even better, the Valentine's Day party.
This is the crown jewel of the whole simulation. It's amazing.
It really is. So they planted another seed, this time with an agent named Isabella Rodriguez. They told her, in her memory stream, you want to throw a Valentine's Day party at Hobbs Cafe on February 14th at 5 p.m.
And that's all they told her, just the desire to have a party.
That's it. From that single seed, the entire architecture took over. Isabella started inviting people she saw at the cafe during her shifts. And then she went a step further. She asked her friend Maria for help with decorating.
And this is where the subplot comes in. We have to talk about the romantic subplot.
It's the best part. So Maria has a secret crush on Klaus, the researcher. This is a detail that was included in her initial 1-paragraph bio seed.
Okay.
So when Maria finds out about this party, she doesn't just decide to go. Her planning module, combined with her reflections about Klaus, leads her to a new action. She invites Klaus to the party. She essentially asks him out on a date.
And Klaus, what did he do?
Klaus accepted the invitation.
Yes. Go Klaus. Finally getting out of the library.
And the really incredible thing here is the coordination required. On the actual day of the party, at 5 p.m., 5 different agents actually showed up at Hobbs Cafe.
And you have to think about the complexity that's required for that to happen.
It's immense. Each of them had to remember the invitation, which might have happened days ago. They had to incorporate the party into their own personal plans for the day. And they had to physically navigate their way to the cafe at the correct time.
And again, just to be crystal clear for everyone listening, there was no party script. There was no piece of code that said, at 5 p.m., move agent X, Y, and Z to the cafe.
Zero scripting. If Isabella had forgotten to tell anyone, or if she had invited people who didn't like her, or if the agents had just prioritized work over the party, no one would have shown up. It was a fully autonomous, emergent social gathering.
That is just wild. It really feels like we are crossing a threshold here from something that is a chatbot to something that is an entity.
It's a genuine simulacrum of a society. But, as scientists, we have to be rigorous. How do we know it's actually good? How do we evaluate something as fuzzy as believability beyond just saying it looks cool?
Right. The vibe check is not a recognized scientific metric. So the paper uses a very clever interview methodology.
They did. They would essentially freeze the simulation at random points and interview the agents. They asked them questions that fell into 5 specific categories: self-knowledge, memory, plans, reactions, and reflections.
Questions like, what are you doing tomorrow? Or who is running for mayor, to test their memory and planning.
Exactly. Or hypothetical questions to test their reactions, like, your breakfast is burning on the stove, what would you do?
And they compared the full architecture against what they call ablated versions, so versions where they deliberately turned off some of the fancy features.
Right. They tested the full system against a version with no reflection, one with no planning, and one that was just the raw LLM with no special architecture at all.
And they also compared it to a human.
Yes, a human crowd worker who was given the agent's bio and told to role play as that character.
And what were the results?
Well, the full architecture outperformed all the ablated versions, which is what you would expect. The no reflection agents were forgetful and shallow. The no planning agents were erratic and inconsistent. But the truly shocking statistic is that the full architecture produced behavior that was rated as more believable than the human crowd workers.
Wait, pause there. The AI was better at being a person than the actual person was.
In this specific constrained context, yes. The researchers found that the human crowd workers often didn't stay in character as strictly. They would get bored, or they would forget details from the agent's long history. They'd say things like, oh wait, am I supposed to know Klaus?
Whereas the AI was perfectly consistent.
The full architecture was ruthlessly consistent. It remembered everything. It stayed in the persona perfectly, because its persona wasn't an act. It was the sum of its recorded experiences.
That is slightly unsettling, but also amazing. It really speaks to the consistency of the machine. But it wasn't perfect. We have to be balanced here and talk about the failures, the hallucinations, and the weird behaviors.
Yes, it was far from flawless, there were definite memory errors. For example, Tom, the guy who learned about the election, he knew he was supposed to discuss the election at the party, but he had a memory retrieval failure and forgot if the party itself was actually confirmed.
So what did he say?
He effectively said, I'm going to the party to talk about Sam's campaign, but I'm not actually sure if there is a party.
A little bit cognitive dissonance there.
For sure. And there were straight up hallucinations. Isabella at one point claimed that Sam was going to make a big announcement tomorrow. He wasn't. There was no basis for that. And another agent, Yuriko, claimed that her neighbor wrote The Wealth of Nations.
Which was famously written by Adam Smith in 1776.
Right. But her neighbor's name happened to be Adam Smith. So the LLM's vast pre-training data leaked in. It saw the name Adam Smith and automatically associated it with the famous book, overriding the actual reality of the simulation.
That's a classic LLM quirk. The pre-training weights are just so strong they sometimes override the specific context you give them. What about their social behavior? You mentioned they were weirdly polite.
This is a really interesting artifact of instruction tuning. The underlying models, like ChatGPT, are fine-tuned to be helpful, harmless, and polite to human users. And that politeness bled into the simulation.
How did that manifest?
You'd have husbands and wives saying things to each other like, it was good talking to you as always, after a simple morning chat over breakfast.
Like they were coworkers ending a polite email chain.
Exactly. I hope you have a productive day, darling. It just lacks the grit and the informality and the messiness of real intimacy. And they were also too cooperative. Isabella got all these conflicting suggestions for her party, and she just agreed to all of them without pushing back. She didn't have enough personality to say no.
And then there were the physical failures. The bathroom incident is a great example.
The dormitory bathroom. It was a small room, designed for only one person to use at a time. But the agents didn't seem to understand the implicit physical norm that an occupied bathroom private.
So what would happen?
You'd have 2 or 3 agents just walking into the bathroom while someone else was already in there.
A bit of a privacy violation in Smallville.
A major one. And it shows that common sense regarding physical spaces is still really hard to convey purely through text descriptions. The model knows the command go to the bathroom, but it doesn't implicitly understand the social rule, wait your turn, unless it's explicitly told.
So we have this incredible, powerful, but flawed architecture. We have a working simulation. What does this mean for the real world? Why should you, listening at home, care about this beyond just, we can make better video games?
Well, the applications are pretty significant. The most immediate one that comes to mind is in social prototyping.
Social prototyping.
Imagine you're about to launch a new social network, or maybe implement a major organizational change in your company. Usually you just have to launch it and hope for the best.
Which can be incredibly risky. If you change the HR policy and half your employees quit, it's too late to go back.
Very. But with this kind of technology, you could model the network first. You could populate a digital twin of your organization with agents that have the same memories and social relationships as your actual employees. Then you introduce the policy change in the simulation and just watch what happens.
You see how the information diffuses? Does it cause toxicity? Does it improve coordination? It's like a crash test dummy, but for social dynamics.
That's a perfect analogy. Then there's the field of ubiquitous computing. Think about the smart home concept. Right now, your smart thermostat is just a fancy timer.
Right. Turn on at 6 a.m.
But imagine an agent that actually knows your life. It has a memory stream of your patterns. It knows you had a bad sleep because it observed you were restless. It knows you have a big meeting today, so it brews the coffee extra strong, not because you set a timer, but because it predicts you need it.
Because it has the high-level reflection that you are stressed out and tired.
Yes. It moves the technology from automation, which is just doing what it's told, to true agency, which is doing what is actually needed.
But with all this power, we have to talk about the risks. The paper itself flags some serious ethical concerns.
Parasocial relationships are a huge one. We already saw how Maria, an agent, formed a crush on Klaus, another agent. Imagine that capability aimed at a human user.
Oh, wow.
These agents are designed from the ground up to be believable, to have shared memories with you, to care about you. People will inevitably form deep, powerful emotional bonds with them.
We're already seeing this with today's simpler chatbots. With this kind of memory architecture, it would be 1,000 times more potent. The agent would remember your birthday, your fears, your mother's name, that joke you told last week.
And that leads directly to the risk of persuasion. If an agent have access to your entire memory stream, It knows your triggers, your history, your political biases. It can tailor a message to persuade you more effectively than any human ever could. It could be the ultimate propaganda tool.
It's an incredibly powerful tool, and like any powerful tool, it cuts both ways.
And that brings us to the final risk, the over-reliance risk. If we start using these agents to replace human users in testing for, say, new products, we might miss out on the beautiful chaos of real human unpredictability.
We'd be optimizing for the AI.
Exactly. These agents are believable, but they aren't human. They're overly polite, hyper-logical approximations. We can't ever forget that.
Well, on that slightly ominous but very important note, we have arrived at my favorite segment of the show.
It is time for Novel Notions.
This is the part of the deep dive where we take the architecture we just discussed and we spin it into something new, something a little outlandish, maybe a little bit dangerous, but technically plausible based on the paper, and the standard disclaimer. This is for entertainment purposes only. Do not try this at home without a fully staffed ethics board review.
Or perhaps just do not build this at all.
I'll kick us off. I'm calling my idea the legacy biographer.
Okay. The legacy biographer. Let's unpack it.
So the paper talks about the memory stream being the core of an agent's identity. Right now, in Smallville, they seed that stream with a single paragraph. John is a pharmacist who loves his family, but what if we seeded it with an entire life?
You mean with real data?
Exactly. We take a historical figure, or maybe a deceased relative. We feed the memory stream with their entire digital exhaust, every email they ever sent, every journal entry they wrote, every text message, every transcript of a video they were in.
And you would rely on that retrieval function, recency, importance, relevance to properly weight their actual life events.
Yes. And you would use the reflection tree to mimic their specific cognitive patterns and ways of thinking. You don't just create a chatbot that sounds like them. You create an agent that lives a kind of parallel life.
So you could ask a question.
You could ask this frozen agent, what do you think about this new scientific discovery that just came out in 2024? And it would reflect on its past work, its stored memories, its core principles, and generate a probable new insight that the real person might have had.
It's a ghost in the machine, but with actual architectural grounding. You could effectively have the agent of a famous author generate lost works in their style based on their life.
Or get specific life advice from your great-grandfather based on his actual experiences during the war. Not generic chatbot advice, but advice rooted in his memory stream.
That is compelling and also deeply haunting. It fundamentally changes our relationship with mortality. If the pattern of your thinking can persist and continue to generate new reflections after you're gone, are you really gone? It decouples consciousness from cognition.
That is the big question. Okay, your turn. What have you got?
I'm going to go a bit closer to that social prototyping angle we discussed. I call this idea the infinite focus group.
For urban planning, I'm guessing?
Precisely. Imagine a digital twin of a real city, not just 25 agents like in Smallville. I'm talking 10,000 agents. Or 1 million. And each one is seeded not with a fictional bio, but with real anonymized census data demographics: age, occupation, family size, income level.
Okay, so you have a high-fidelity simulation of Seattle or New York or London.
And you want to test a major civic change. Let's say you want to rezone an entire district, or change all the bus routes, or implement a new tax policy. Instead of doing a survey, which is notoriously flawed because people often lie or don't really know what they want, you just run the simulation.
You let the agents live through the change for a while.
Exactly. You change the bus route in the simulation. The agents have to navigate it. They have to use their planning module to get to work on time. You run the simulation for a simulated month, and then you interview them.
You use the exact interview methodology from the paper.
You ask them, are you happier now? Were you late to work more often? Did you see your friends less this month? You could detect these subtle, second-order sociological effects, like a sudden drop in neighborhood cohesion because the new bus route bypasses the local community center before you even break ground in the real world.
It's like playing SimCity, but the citizens have souls. Or at least they have reflection trees.
It grounds the pathfinding and environment tree concepts described in the paper, but it scales them up to test real sociological theories. It could revolutionize governance, or it could lead to a technocratic dystopia where we optimize cities for the happiness of AI agents, not actual humans.
A very fine line indeed. But I guess that is the power of this architecture. It moves us away from static data and into the world of dynamic, believable behavior.
It really is a glimpse into a future where our digital environments are not empty, but populated with entities that have their own lives.
Well, That is all the time we have for this deep dive. This paper, Generative Agents, it really feels like a turning point. We move from simple chatbots to agents with lives.
It really is the beginning of a new era in AI interaction, a foundational piece of work.
This has been Talk Tensors. Check the bio for a link to the paper. Keep your gradients steady.
And your loss functions low.
See you next time.